Hi guys, in today's video I'm hoping to demonstrate how to model a simply supported beam with multiple loadings using Spacegass. Here we have a typical ground floor framing plan. I have sectioned it off for clarity. The aim of this exercise is to design the beam B2 using Spacegass. As you can see, B2 has partial floor loading as well as the point load from B1. The dashed line represents the direction of the floor joists. As you can see here, the floor joists going left to right of the page are supported by beam B2, B4, lintels L3 and L4, and then we have the floor joists going up and down the page, and they are supported by beam B1 and lintel L1. And of course, the reactions at the end of B1 are then transferred to beam B2 and the internal wall on the other side. L2 and B3 are just supporting the upper wall loads and roof loads. Sometimes we can use double joist instead of L2 and B3, but also note that L1 and L3 and B4 as well may support wall and roof loads depending on the position of the windows on the upper floor. Okay, all the L members are positioned over the window head, and this is why we generally nominate them as lintels. From a drafting point of view, it is always a good practice to nominate these lintels with a clockwise pattern rather than just random numbering on the plans. This makes it a lot easier for the engineer who is checking the job. And it makes a minimal room for any errors. So as you can see here, we start with L1, then clockwise go to L2, L3 and L4. The other tip I have is always number the external lintels first and then proceed with the numbering of the lintels over the internal door heads. Then we have the beam members such as B1, B2, B3 and B4. Beams are generally positioned in the floor space. Sometimes beams that are also positioned in a bulkhead, we can call that a beam rather than a lintel. Lintels, are generally nominated for members over a window or a door head. Now, have a think of why I numbered the beams B1 and B2, or why have I drawn it up that way, that particular configuration. Well, very simply put, to design B2 we need to first design B1, and hence this is why I drafted it. So then the engineer who's checking the job and is going through the documents would first go through B1, find out all the reactions, and then take it down to B2, and that quickens the process of design, and there'll be minimal errors. Okay, let's get straight into it. To model beam B2 on Spacegass, we first need to determine the applied dead and live loads, and then we will work out the loading combinations that is required and different case load case combinations. Okay, here now we have the loading table. So to design beam B2, we need to work out the partial loading from the joist that's running left to right in this area here, and I call that as W1. Okay, and then we have the load on this side here from this joist, and that can be W2. So we need to work out the dead load and the live load, and the floor load width. So as you can see, this side here of B2, we have a floor load width of 1.75, which is basically half the distance between that point and that point where L3 is. So that shares the load. Half of it will go on L3 and the other half will be on B2. So the floor load width is 1.75 for this side of the beam of W1. For this side of the beam of B2, the floor load width then will be half the distance between L3, that wall where L3 is supported on, and B2, plus half the distance between the internal wall and B2. So it's that distance here. and that will be 3.9. I've set up the table like this to make it easier. So W1, simply the floor load, which floor load width is 1.75 like we said before. And for W2, the floor load width is 3.9. And we also have P from the dead load and P from the live load tracked down from beam B1. That was given to us in the example, okay, which is 3 kilonewton dead load and 4.5 kilonewton live load. Alright, the dead load, the floor dead load alone is 0.43 kPa. Okay, you can get that from 1170, AS 1170, and there's a lot of information there about the floor loading. The floor live load is 1.5 kPa, 5 kPa. Then we find out the UDL load. We need to find out the UDL load, which is W1 and W2. How do I find the UDL load? Well, I multiply the floor load width by the floor loading for the dead and for the live. Okay, so in this case, floor load is 1.75. You multiply by 0.43, you'll get 0.74 kilonewton per meter UDL load, dead load. The live load is simply 1.5 multiplied by the floor load with 1.75, and that would be 2.625. Okay. W2, you have the floor load width of 3.9. You multiply that by the dead load 0.43 of the floor, and you will get 1.66. Same as the live load, 1.5 multiplied by 3.9 is 5.85. It's an easier way to do and to set up a table like that. You also have the dead and live from the point load, which is just simply 3 and 4.5. Then we need to work out the loading combination. Okay, we need to work out the loading combination for strength and for serviceability. In strength, bending, shear and bearing is what we need to look at, and for serviceability, mainly deflection and sometimes vibration as well. The long-term deflection with the long-term factor, the combination factor is 0.4 that we're using in this case, and the deflection shall not exceed L over 300, and this information is back into 1170.0. So you can go back, AS 1170.0, you can go back and get more information about that. So we set up the table for this loading combination, and we have 3 load cases here. For strength, 1.35 G. So we worked out W1 to be 1 in terms of the dead load only, and W2 is 2.24, and the point load is 4.05. Again, for strength, the other loading combination is 1.2 G plus 1.5 Q, 4.83 for W1, 10.76 for W2, and 10.35 for the point load. And then finally, for deflection, will just be the dead load plus 0.4 times the live load. So what we need to do after this is go on Spacegass and input these values into this beam model here. Okay, so we'll go through this beam model in Spacegass, work out the bending moment, or the worst case bending moment, worst case shear, and deflection for these load case scenarios. Okay, bear with us and we'll go to Spacegass right now. Okay, now we're in Spacegass. The first step is to plot all the nodes so that we can draw up the beam. So we got a structure, and then we come down here to nodes and datasheet. Node number 1 is 0, 0, that's at the beginning of the beam. Number 2, where the UDL is W1, that's going to be 1.7. And number 3, I introduced another node to get a more accurate results. and I put it at the midspan of the second span. Made that to 3.45. And then the last node 4 would be x is 5.2, which is the total length of the beam. And then press OK here. Right, now we have the nodes drawn up for us down here. Second step is go down to this pencil here to draw the member, starting from left to right. So you click on it and go from node to node. So we did the 1.7 and the 3.45 and then the 5.2. Okay, now it's time to to draw in the supports. So you come here with the left click and then the right click and then press properties at the support here, so at the ends. So then press properties and we will make this as pinned. This little button here and press OK. On the right side it's going to be a roller so that it can be statically determinate. We do the same thing. So we come here and we do left click and then right click and then properties and click the roller support here. Great. Now it's time to draw in the loadings. Okay, W1, which is that span here, and W2 takes these two spans. So we'll do W1 first with the left click and then properties. Actually, before that, we can do the, okay, so we will left click and we'll say member distributed forces, okay, before we put the beam sections in there. So member distributed forces, and we will put this under load case 1, okay, and apply the load cases, apply loads to all selected members, press OK. And what is load case 1? Load case 1 was the 1.35G. So W1 will end up being 1. We come here and then we type in -1 kilonewton per meter. Minus because it's going down, and press OK. And then this span here, we'll do the same thing, member distributed forces. Now that's going to be the W2. It's still under load case 1. And what is W2? W2 was 2.24. So we come here under the Y minus 2.24 kilonewton per meter, and it ends at 2.24 kilonewton per meter, and press OK. Alright, now it's the point load time. The point load is at the end, at this point here, at 1.7 meters. So we come close to it, click it with the left click and then the right click. Then press node load. It should be somewhere here, node loads, right here. Again, it's under load case 1. Apply loads to the selected nodes, press OK. And what is the node load in this case? That was 4.05. So we come here, say minus, again minus because it's going downwards, minus 4.05. Now we have all of the loads are here. If you want to see what they are, you can select here and you'll be able to see W1 and W2 loadings. Okay, so what I did was I turned on this little bubble here, and then I came onto this point and I said show hide diagram. Okay, here you hide it. If you press it again, you get to show all the loadings. Alright, now it's time to do load case number 2. Select the first span, say member distributed forces. This time we're going to put 2 for the load case and press OK. Now what is load case 2? 1.2 G plus 1.5 Q. W1 is 4.83 kilonewton per meter. That's good. Okay, we come over here and put under the Y. So that's minus 4.83 and press OK. Then we select the second span. We will do the same thing, member distributed forces, apply loads, same thing under load case 2. And what is W2 is 10.76. So we come under here, minus 10.76 and press OK. Finally, the point load, which is here. And then put, with the right click, put node loads, still under load case 2. Press OK. In the Y direction, and the load was, the point load was 10.35 minus 10.35. Press OK. The last load case, which is for deflection, serviceability, G plus 0.4 Q. Select the first span again. Member distributed forces. We will call this load case 3. Okay. What do we have? 1.79 for W1. Okay, 1.79. We'll put it in. Minus 1.79 kilonewton per meter. Continues 1.79 throughout the span of 1.7 meters. And press OK. Second span. Member distributed forces. Keep missing it. Here it is. Member distributed forces under load case 3. Press OK. And I think this one is 4 kilonewton per meter. Minus 4. Press OK. And the last step is the node force, the point load, which is here. And press node loads under load case 3. Okay. And what have I got here? 4.8. Minus 4.8 kilonewton. And press OK. Now the following step, after we finished all the load cases, it is important to name them. A lot of times we forget that. So how to name them? Important to name them. Over here we can see that it's got unnamed load cases. So that can be confusing. So to name them, we can just go to loads up here and then load case started, that's all. Okay. Over here, case number 1, and give it the name, which is 1.35 G. And type over here, so you can go to the second one, load case 2. It will be 1.2 G plus 1.5 Q. And then over here, type number 3. That will be G plus 0.4 Q. So here we've got all the load cases, one which is 1.35G, 2, 1.2 plus 1.5Q, and load case 3G plus 0.4Q. Press. And we have finished this. Press OK. If you look up here, we can see all the load cases now, 1, 2, and 3. Okay, now it's time to provide a section property. So we select, like with the left click, we select all the members. You can do it that way individually, or you can highlight the window around the whole entire structure and then say select members. Okay, I find that a lot easier to go around anti-clockwise around this whole structure like this and then select member. Okay, with the right click, we go to properties and we select these two. I usually start off with the property and the material property. So we go to the library here and I will choose steel. Look, there's concrete, aluminium, and there's also timber as well. But for 5.2 meters with that loading, most likely steel will work. So you press steel and you can double click on that. And it automatically gives you the Young's modulus and the mass density and the temperature coefficient and all of that. So, and then now we select the section capacity or the section property. The library function is here. And universal, I would use a UB, a universal beam. So you select this first one here. Let's try 200 UB22 for argument's sake, and we'll see what happens. So we double click on 200 UB22 and then press OK. Okay, so we have the section properties in there, the material properties, and all the load cases and the supports at the end. I like to select on the supports here just to make sure that I've done it properly. So if I select up here, it shows that the left hand side is pinned and the right hand side would be a roller. Okay, now I've got all my load cases in. One thing I need to do is to add the self weight of my beam. To do that, you go up to this button here, self weight, click on it, and you have cases. We'll start with number 1, we press 1 and we type here -1, yes, because it's going downwards, the acceleration is going down. So we do the same for case 2, we add the self weight, it's -1 in the y direction. And then we type case 3, it's also -1. That means we've added the self weight of the beam to all the load cases. And then press OK. Okay, checklist is complete. All the combinations are in, the supports are in, the point load is in, and I think it's ready to be analyzed. So we say analyze, linear static analysis, and press OK. Great. Now, first thing I usually go to is deflection. So load case 3 is a deflection for serviceability. Click on that and click on the deflection, and you can see here the deflected shape, and we have 9.67 and 9.7 around this node that we made. We should have done another node maybe here somewhere. So overall it will not exceed 10 millimeters. The allowable is over 370 millimeters, but we always try to keep the deflection below 10 millimeters. The 200 UB22 sounds like a perfect beam to use. We now go to the loading combination of 1, which is 1.35G, and click on shear and moment. So if we click here, this is a moment. You can see that the maximum bending moment for that load case is about 10.75 kilonewton meter. If we want to check the other load cases, 1.25 plus 1.5 Q. That is much worse here, 38.74. Okay, here's 36 at that node that we introduced. So maximum around here, this area here would be about 40 kilonewton per meter. And we need to check if that steel beam works for 40 kilonewton per meter. To check the shear capacity, select on this one, that's for shear not the shear capacity, the actual shear force in the beam. Check the shear force, select on that, and you can see here that this is the shear force is 30.29 at the ends, and at this side here you have where are we, 27 kilonewton at the left hand, and it goes all the way down to the point load 18.5 and right 30.29. so maximum shear is 30.29, but when we design the beam we take it as D, or the depth of the beam away from the support, so it would be around here somewhere. So V star worst case scenario is 30 or 31 kilonewton. And if we try the other loading combination, which is 1.35G, it's a lot less, 7.38 to 7.36. So most likely this loading combination wins, number 2 wins for strength, for shear and moment. For shear and moment, and I think the moment, what did we say the moment was? About 38.74. Assume it's 40 kilonewton applied, kilonewton per meter applied moment. Okay, so I hope you enjoyed this, and yeah, and have a great afternoon.